everyone. I'm afraid you kind of derailed my initial joke, but I'm going to make it anyway. No worries. So I'm going to talk about transformers. But not that kind of transformers. I'm going to talk about monad transformers, but not about that kind of monads. Rather that kind of monads. And we've seen some of these diagrams today, so I'm not going to bore you with these details. I mean, seriously, it's 6 p.m. in the evening. We're not going to deal with categorical diagrams or something like that. We don't just do that. And this is not because I don't even understand them. But so yeah, monad transformers. And to give you the bottom line of what a monad transformer is right in the beginning, I couldn't put it more concisely than Patrick. So you take effects from one monad and put them into another monad. That's what monad transformers are. Right. So when initially writing this talk, I thought, okay, so monads are probably like, common concept these days. So if you went to a conference 5 or 10 years ago and said like the M word, everyone would blankly stare at you. Like, no idea what you're talking about. But these days, many people have already heard about monads and know to some extent how you can use them, not necessarily what the theoretical underlining is or something like that, but you can probably write some code which uses flat map or bind, or I don't know what's it called in F#, but we've seen monads in F# today or something similar. Anyway, so monads, they're already there, so people use them. And, but there's some more interesting stuff behind them, not just theory, but also some practical stuff, which is kind of derived from them, or where monads build on top of them. And this is the hierarchy composed of functors, applicatives, and monads. And in this talk, before I'm actually going to start with monad transformers, so you can see monad transformers are only the final third of this talk, I'm going to give you the idea of what this hierarchy from functors to monads is. So we're going to start from nothing, and then we end up with monads, and then we can put monad transformers on top of them. Right. So as I said, everyone knows monads, and let's have a look at what monads are actually being used for. So of course, there's error handling. So if you write a web application, for example, which talks to a database or to some other external API, which runs on AWS or something else, then you have plenty of points where your code can actually fail. And as we've learned today from John's keynote, we actually want a single point of failure in the code, and then we want to handle all the errors in one place, where we could potentially distinguish what kind of errors they are, but we don't want to litter our code with try-catch blocks all over the place. And monads can help you there. If you have failing computations which can potentially fail, monads can give you a way to express that if this computation succeeds, then continue with this other one, and then only at the end you deal with all the errors which could have potentially arose. So other thing is parser combinators. So if you've been writing not necessarily a compiler, but anything which consumes non-trivial user input, you might have been doing that by hand. So you wrote probably a function which is called parse, whatever, and then you make a case distinction on what the first character is and do something like that. And there are many ways to do how to do parsing. So and many old things how to do parsing. So parser generators like Yak and Bison and Lex and whatever they're called, they've been around for a long time. And in the functional world, we use parser combinators. So essentially, you're just writing an expression which describes how to parse something. And this is very elegant, and it's also monadic. So yeah, and then you can do value-oriented parallelism. This is essentially a fancy word for futures. So a future of T is essentially type, which represents a rounding computation somewhere in the background on a thread or on some cloud service or in your database or whatever. And then at some point, you can actually do something with it. But there's an important thing: you can never get this T out, only at the end of your program. But you can work with this T as if it were there. So it's kind of an abstraction. You say, okay, I have a value somewhere in there, and then you can compose this with other values. So say I collect this from my database, and I collect this from my web service, and I can smash them together. And my future class or future monad deals with how to compose them together. So monads have quite a lot of use cases, and yeah, the slide says if all you have are monads, then probably every problem looks like it can be solved with monads. But that's actually wrong, because code using monads has both mathematical and practical limitations. So what do I mean by that? And let's go to demo. So please have a look. Is this big enough for everyone? Okay, great. So I've defined a very simple function. It takes a string and produces an either string of int or int. So either is a type which can have two values. It can be left or right. And this is kind of silly naming, I guess. But the convention is that right means right. So if you get the left, then it's wrong, and if you've got a right, then it's right. Okay, so just to say, I mean, this looks simple enough, right? So you have a try catch, and you call toInt on the string, and this toInt is from Scala, and unfortunately it throws an exception, but we don't want to deal with exceptions. So we put this in the try catch, and then say catch with this number format exception, we give back a left, so we have something wrong, and we give back the error message. Of course, in real code, you wouldn't put your error message in a string. You would put it into some more detailed data type describing where the error came from or something like that. But that's beside the point. So you have this function which takes a string and attempts to parse it to an integer. And we can use that now as a monad. So we can first load this. We can load this into our REPL, and now we can say string to int, and we give it a string like 1, and it will give us right 1 because it's actually a number. And if we put something wrong here, then we will get left invalid number. Simple enough. So Scala has this thing called for comprehensions, and other languages call it monad comprehensions, and I already forgot what F# called them. Can you help? Computation expression. Okay. Thanks. So we can do multiple of these computations and join them together. And let's say we have two strings which we want to parse. So we would write for, and then we say, okay, x is this one, string to int 1, and y is string to int 2, and then we want to yield the sum of them, so we want to add them together. And any Scala programmers in here? So this is the next question is just for the Scala programmers. Does it compile or not?
No.
Why not? Yes. So to everyone who's not a Scala programmer, this is just what I'm going to type now. Is just because Scala standard library is sometimes not very intelligent. So this is just to make it work, but you can ignore that. So now we have parsed those strings, and we get a correct value. So it's it's right 3, and that's already nice. But what happens if one of them is a failure? So let's say we replace the 2 by an A, then we also get the failure. So now what happens if both of them are actually failures? So if we have both numbers are not actually numbers, then what we get is we get the first error and just the first error. And this is already hinting at the problem with monads at this point, because there is no way you could implement this type such that you get both errors. Now imagine you have a web service, right? And this web service requires a user to enter a form, like name, address, and something like that, and birthday or whatever. And so the user now types in something like name, address, and hits on send, and the web page returns and says address is wrong. Now the user goes ahead and fixes the address and press enter, and now it says birthday is wrong. So why didn't the web application tell me earlier, right? I mean, there's a bunch of failures in validation, so why don't you tell me in the first place? And this is probably because someone didn't thought through how to implement this correctly. Okay, so now that you've seen the problem with monads, and this is basically also the problem which you would get with imperative programming if you would fail early or something like that. Now let's try to think about how to fix this. And the next slide is for German-speaking people only. If you don't speak German, you can come up to anyone who speaks German to explain this joke. So we're talking about functors. And functors are essentially things which have a map function. So where you have a piece of data or multiple pieces of data, and you can transform them using a function. And this is also what Java 8 has now. I mean, virtually every language which takes itself seriously has some sort of map functions around. So you have a list of 1, 2, 3, and you map +1 over it, and then you get 2, 3, 4. So that's simple enough. So now you have the option type, you have sum of 1, and you add 1 to it, you get sum of 2. And if you have a future computation, something asynchronous, and you map 1 plus 1 to, then I can't really print that because it's a running computation somewhere. I can't really print that out. So this is something which eventually will become 2. So what is interesting here is that if you map over something, you always have the same shape as before. So you put something in here with 3 elements, you get something with 3 elements. There's no new elements or removed elements or something like that. It's always the same number of elements. And here, if you have a sum, you get a sum back. So there's no way you could get a none here, or if you have start with a none, get a sum. So essentially the idea is that functors are about transforming data, but not shape. The shape stays the same. And there's actually a very rich theory behind this kind of shape stuff. So if you're interested in that, look for Google for Haskell traversable and shapes and containers and something like that. These are just a couple of keywords, and you will find very interesting papers about this. So now the cats library in Scala offers a generalization of that pattern, and obviously Haskell also does. This is called a functor. So a functor is essentially everything which implements this interface. So which can give you a map function. In Java terms, it would probably be called mappable or something like that. So everything you can apply the map function to. And you start with something, some container or computation f of a, and you get a function from a to b, and you transform it to an f of b. So that's easy enough. That's the most fundamental tool we have to abstract over several kind of data. And here's a caveat. Please don't think about this f as some sort of container of data, because that's wrong. Containers are just one use case. Futures are another use case, and I think you could hardly call future a container of data. It's just a representation of data. So you have just one idea of data, right? It's a computation which eventually will give you data, but it's not a container, right? So whenever you read something like monads are just containers, that's nonsense. Please don't believe that. Okay, so now we have functors, but we can't do really much with them. We can't just map over them. So what if we tried more power, right? So let's add something on top of that. Okay, so the next level here is our so-called applicatives. So I can't really tell you why they're called applicatives. I have no idea. And we just accept that name, please. So applicatives are about transforming independent pieces of data. So you have one piece of data over there. You have another piece of data over there. They have been created completely independently. They can come from different things, from different places. And then you can join them together and do something with them. And applicatives offer a function called map2. And this name is really apt, because you take 2 inputs of the same type. They can have arbitrary shape. And then you give a function which takes 2 arguments. So this is Scala syntax for creating a pair. And this essentially creates a list of all the possible combinations of these 2 values, right? And you can already see that it's independent, so you get all the possible combinations here. This is what the applicative instance for lists does. And this is really nice, because now you can have 2 different data sources, and you can join them together in some way. Question? And of course, you can abstract over that. So that's the applicative class. And every applicative is also a functor. So you take a functor and add something to it. I see you looking funnily. This is not the whole truth. So it's roughly applicative. It's not quite, but just, yeah. So it takes the functor, which has a map function, and it adds another map2 function, right? So it's it's in the same spirit. It's just one more thing. And it takes an f of a and an f of b, and it takes a function which takes an a and a b and transforms it into a c. And again, there are a couple of laws there, and there's some intricacies on how this is to be implemented, but just assume for now that people have thought about how to implement this, and you can implement this for lists, and you can implement this for futures, and you can implement this for option, and for many different things. Right, so the idea about applicatives is you can take 2 different pieces of data which have been created independently and then munch them together. Right, so still no monads. What if we tried even more power? So this is probably code you have seen before or have written before. So you have your deep down in the business logic of your application, and you have to do, like, a user comes along and wants a file, right? So you have to, first you have to ask the database, okay, is this user even allowed to read this file? So you get some access token from somewhere, and then, you know, depending on this token, you can then call the database interface to, you know, give me that file, and then you send the header, and then, I don't know, something happens. So the interesting bit here is that this line, so the second line, crucially depends on the value of the first line. So you cannot execute the second action before the first action has been completed. And same for here. So, okay, so this one is actually independent, but anyway, so this line is crucially dependent on the result of that line. So you can't execute it. So you have to execute it sequentially, right? So if you've ever written future code in Scala, and you had something like this, where the lines were actually independent, you were probably wondering, why aren't these futures running concurrently? Like, why are they running sequentially? Now, the reason is they have to, because in this syntax, the compiler can't figure out that they're independent. So whenever you do this for and then yield, and you have the sequence of monadic operations which get compiled down to flat map, the compiler has to enforce a sequential ordering because there could be dependencies. So monads are about transforming dependent pieces of data. So you get some data from some place, and then depending on what data is, you create another piece of data, right? So you get this token from somewhere, and then depending on the token, you can read the file, and then depending on what you read, you can send it to the user via HTTP. Okay, sounds fair enough? Okay, and this is the same thing I did in the first demo, where I used the for comprehension, and now it becomes clearer why you can't give both errors, because you can't actually execute the second action because the first one failed, and the second action could be dependent on the first one. Right, so monads, you can also write them down, and monads are applicatives. So you take applicatives which are functors. So you have functor, you add the map2 function, and then you add the flat map function on top of that. And it takes an f of a, and then it takes this a and gives you an f of b. Right? So this is kind of a sequential composition. So this flat map function gives you access to whatever's in there, or whatever's going to be there. Right? So if I told you about this, functors are not containers, so you basically have something, or a promise of something, or just a representation of something, and the flat map method gives you ways to deal with that without actually getting the value out. So if you call flat map, you still are in this type context. So you still have this f around it, but this flat map function gives you access to this a inside there. Now, what's interesting about monads is that once you have this flat map method implemented, you can actually implement the map2 function. So essentially, if this function is really powerful. So once you have that, you can get the other one for free. Now, who here thinks they can implement this in less than 10 seconds? Less than a minute? Okay, so how is it implemented? You have 60 seconds, 59. No, it's actually not that complicated. I'm going to show you the code, and you will see that the structure is really simple. So you start with the FA, you call flatmap on it, which gives you access to the A, and then you apply flatmap to FB, and which gives you access to the B, and then you just call the function on A and B, right? Make sense? Anyway, so let's go to another demo.
Can you write it in terms of for comprehension?
Yes, okay. I could write it as a for comprehension, but because of Scala, I can't do that easily. You have to. The flat map must be a method on the object. This is a method of the type class. Okay, let's put that to practice. So now let's assume we are going to write this website, or we have this website which gives this completely stupid error behavior, and we want to fix it, right? So the user enters something wrong, you click on send, and then it should print everything what is wrong in the site. So we're now going to fix this. Okay. What's it called? So now we are going to use a specific type from the cats library, which is called validated. And the name already tells you what it's being used for, namely for validation of input. And as you can see, the structure is really similar. So let's go back to this one. You have this try catch, and then in the correct case you do something, in the error case you do something else. Right, so now the functions are not called left and right, they are called valid and invalid, which makes sense if you're in a validation context, but in essence it's the same thing, right? So okay, so we are going to load this one. And now we have another string to in function, and we can call it just for fun. We can call it something correct, and you get valid 1, and we can call it something incorrect, and we get the invalid case. So far, nothing interesting happened. Okay. Now let's see what happens with the for comprehension we had earlier. So we had this for comprehension, and now I'm going to remove this right here because I'm not going to need it. So let's see what happens here. And we see flat map is not a member of validated. So this validated type does not offer the flat map function because it is not in fact a monad. As I told you, once you write it like this, there's no way to recover all the errors which happened. So Scats is smart and doesn't even offer you the facility to write it like that. So you have to write it differently. I'm going to write it differently for you now. So we're going to list all our inputs, and now we're going to use a very fancy operator. This operator has multiple names. I know at least the Home Alone operator, the Cinnabon operator, and the TIE Fighter operator. Call it whatever you want. I call it the applicative operator because it's the defining operator of applicative. So we're just going to use the applicativeness here. And now we are going to call this map2 function. And as before, we are going to add these two pieces of data together. Okay, it is actually .map and not .map2. Sorry about that. Okay, so now we have the same behavior as before. If everything's valid, we get the valid result. Now, what happens if we do something wrong? So let me destroy this. So we get one error message, and if I destroy both, I actually get both error messages. Now you're probably going to tell me, like, what is this? I can't use this. This is just a concatenated string. Like, you know, this is not helpful. What you would do in real code is you would put, as I said, you are not going to use strings for your error messages. You're probably going to use some other data type, and you're probably going to use a list of errors, and then it would work as you expected. This is just for demo. So in the stupidest case, it uses just string concatenation, but you can use whatever data type you want, and you can implement this as well. Now, what if I'm going to tell you that you can do that for an arbitrary number of arguments, and you can do that for a number of arguments which are not even known at compile time? And we can do that with lists, actually. So let's say we have a list of values, and now we're going to apply a fancy operation, and I'm not going to explain to you how it works. I'm just so much as u means you've got nothing to see here. Of course, I'm kidding. You can read this. You can read this up. It's not that complicated. And now I call the string to in function on each of them, and then some magic happens, and you get a valid list of 1, 2, 3. Now, if I destroy here something, B and C, I get no list back, but I instead get all the error messages which happened. Right? So we can even deal with arbitrary user input, essentially. Okay. Yeah? Here?
Shouldn't that second one be a map? Because F is giving me a C, the second flag map?
Yes, you're correct. Okay.
That's why I earlier.
Okay,
So,
yeah, you're right. Thanks. Okay, so now let's get closer to the actual topic of monad transformers, and let's talk about composition. And essentially, we as programmers, we are machines which turn coffee into abstractions. So we could write all our programs in assembly. We could write all our programs in C, but obviously we at Lambda world, so we are using higher abstraction, so we write our programs with lambdas. Actually, Lambda calculus is older than assembly, which is kind of funny. Anyway, so we program and we abstract. So this is inextricably linked. But on the other hand, we can invent all sorts of abstractions. So in a sense, the factory pattern is also an abstraction. But we don't like this pattern because it's not composable. So we want abstractions which can actually compose together. Yeah, because non-composable abstractions are useless. So functions, for example, are the simplest composable abstraction ever. Because if you have a function from A to B and a function from B to C, you can just compose them. There's nothing you have to do for that. It's the easiest kind of thing to do. Okay, so let's say you have a function which converts it into a string, so the other direction, and you get the list of ints, right? And you want to convert every int in there, so very deep. You go deep into this list, and you want to convert every int to a string. So how would you do that? So the simplest way, which could possibly work, is to call map inside a map. But there are actually ways to do that smarter, in a smarter way. And here's another demo. So let's say we have, wait a second. Okay. So as I said, so we can say list 1, 2, 3, and in Scala this toString function is actually just called toString. So we could say map toString. Right. So we could also use some nested for comprehension, something like that, but essentially we would just nest these map functions. But that's stupid, because once we get into deeper nesting, so let's say you have a real application, you probably have a future of a list of options or something like that. And writing these nested maps quickly becomes tedious. So functors compose. So what you can do is you can write functor of list, compose functor of list. And now you get something fancy. And this actually means that you have a twice nested list, and you can map over this inner thing. So let's save this functor for later use. Let's say val f, let's say call it ff, functor list and functor list. And now we can say ff.map. And we can now take a list of 1, 2, 3. And we can call toString on it. Right. And now we just needed a single map, and it would traverse the whole structure for us. And this is really nice because you can compose anything with everything else, which is a functor. So if you have like a functor of list, you can compose it with a functor of option or something. Right. So whatever nested data structure you have, if any layer is functor, then you get a functor for free, essentially. And this is nice because, as I said, you don't need to nest all these map functions. Okay, so surely we can also compose monads, right? No, we can't compose monads. So there's no compose function on monads. So that's the talk, sorry. But we can't do it in general. So there's no one preventing us to try it for special cases. So now finally, I'm going to talk about monad transformers. Welcome to my talk. So what do we have? We have flat map functions for our inner and our outer thing. No, this is the inner thing, that's the outer thing, anyway. And we want to get combined flat map functions. So let's say f is future and g is option. So you have a future of option, of asynchronous computation which might fail. So you have a future of option, and then you have a function which takes an a and gives you a future of an option again. And now you want to get back a future of option. And you could, of course, implement it with a nested flat map and a case distinction on this option and whatever. And we have these two things, and we want to get that. Now, quick interlude of computer science. The halting problem is a very interesting problem. It's very old, and also it's one of the problems where we know the answer exactly. So the halting problem means that it is undecidable whether a program will terminate on a given input. So it is impossible to write a program which takes another program and says yes if it will terminate and no if it won't. And this is a very basic result, and it has been proven in different ways in the last century. And it's a very clear result. So if someone claims they have a programming language which only accepts terminating programs, they must be lying, right? But these programming languages exist, for example, in Idris and in Acta. So what do they actually do? So what they do is they try to guess, right? So they make an educated guess and they say, okay, this looks like it definitely terminates. I can prove that it terminates for whatever reason, so I accept this. And here I have something where I have no idea what's going on, so I'm just going to reject it. It's also like user input validation. So there might be strings which are safe for your database, but which you will reject anyway. This is, for example, like every other website which has password criteria, like it must not contain this letter or something like that. It would be fine for the database, but they just don't accept it for whatever reason. So they just make a guess. So they say, okay, I only accept these sets of characters. These are fine, and the others I just don't care. And this is what some programming languages do. They analyze the program, and if they can definitely say it terminates, then they will accept it. And if they can't, they will yell at the user and say, fix this, please. And then I can accept it, even if it might terminate at some point. So it's the same as for type systems, really. So there are programs which are well-typed, which don't go wrong at runtime, so where you don't get the type error, but the compiler still rejects. Analogy clear? So if something is undecidable, it doesn't mean that we can't try. Okay, so what do? We specialize our problem. So we're now trying to analyze special cases. And we're going to compose particular monads. So as I told you, imagine this G type is option. And now we say, okay, we specialize our flat map function for options. And maybe we can make progress here. I mean, I don't know. Let's just try it out. And if we can make progress here and we can solve that, maybe we can get some insights into when it's actually possible and when it's not possible. All right, so more demo. Okay, so as I said, I'm always going to use this. I'm going to specialize this for options, and this is exactly the type signature I showed you in the slides. So we need to implement this here, and just for some use cases, we could, write a function which takes an integer and checks which factors are present, and this would return a list of option of int. Or we could have an expensive computation which does something which returns the future of option of int, and we want to compose these together in a for comprehension. Okay, so we have written these functions and they return this, and now we just need to implement this flat map to make it work. Okay, so what is the stupidest thing that could possibly work here? So we could just try flat mapping with f. So f is the only function we have here, and we could try putting it in a flat map. And we could say, okay, FOA, which is an f of option of a, and then flat map f. And just let's just throw it at the compiler and see if it eats it, and if not, what it tells us. So we're going to load this. Okay, so there's a type mismatch. So what have we given it? We have given it an A, turning into an f of option b. But it wanted something which took an option of A and gives you an f option b. And now if you look closely, you see that the return type is already correct. So the return type is already something what we want. But the argument type is wrong. So it wants us to deal with an option of A, but we only dealt with an A. Now, if you get an option of A and we need something for A, what can we do? We can pattern match on it. So this is the only structure we have an option. This is the only thing we can do now. So we can analyze what we actually got here. And this, what I'm going to show you now, it's called TDD, type-driven development. So what we can write here is we can write a case. If in case we get a sum of A, or we get a none. So this triple question mark is just undefined. It just shows an exception. Okay, let's ask Mr. Compiler. Okay, type checks. So that's already a good idea. So what we did must have been somehow right, but now we just need to implement it. Okay, so what can we do? So if we get a none here, we don't actually have an A. So we can't apply this function. So we need to give back the none in some way. And the only thing we need to do is we need to put this none into our f. And there's a function for that. It's called pure. So we can look at the monad for f, and we can call pure on none. And I think this needs a type description because Scala. Let's check. Okay, so this works. So the none case is correctly handled. Now 90% done, 90% remaining. So what is the type of this A here? So we have the sum A. What is the type here? A, right. And do we have something which can deal with an A? Yes. So what can we do? Yes. So can that possibly be it? Yes. So we just took the A, put into F, and then it works. Okay, so let's have a look again at this code. So essentially what we're doing is we're doing a case analysis on what we get. So if we have some value, we just pipe it through the function which we wanted to apply in the first place, namely F. And if we have got nothing, we just need to give back some base case again. So essentially we are mirroring the structure of the input and giving it back in the output. Make sense? Now we can actually try this out. And run some of these functions. And since factors present is kind of boring, we are going to use this expensive computation. By the way, does anybody know what this computation is? Yes? Yes, collards. So it's actually unclear whether this, if you change this, whether it actually terminates. It's suggested that it will, but we haven't found a proof yet. And with we, I mean humanity. So I can say expensive computation. Now it's actually in func.expensive computation. And I can run it on 5. And I will get this future thingy, which I can't really print, but I can ask whether it's completed. Is it completed? Yes, so I can ask for its value. So it's 16. So it's sum 16, right? So please ignore these outer type constructors. They are from Scala. Now we can try to compose these expensive computations together. So we can say flat map for option. So we take an expensive computation of 5. And what do? We apply this expensive computation again. What did I do wrong? Sorry? No, it's actually wait a second. Ah, the order is wrong. Okay. Sorry about that. So we first take the function and then the argument. What was I thinking? Yes. So this works now. So we can apply 2 steps of our expensive computation. Okay, let's do that again. And we can ask if this is finished, is completed. Yes, it is. So we can ask for the value. And now we have applied 2 steps. So we went from 5 to 16 and now to 8. And we could repeat that ad infinitum. Of course, now you're saying, well, this is kind of stupid because now I can't use this for comprehension again. But there's actually a fix for that. So you obviously don't want to call the flat map for option function again and again. So there's this class, and this is now our actual transformer. So an option T is nothing more than a wrapper around an M of an option of A or an F of option of A. So that's basically it. For Haskellers, a case class is a new type, and for MLers, it's just a data type with one constructor. And we can implement this flat map function here just as I showed you before. The only difference is that we have this wrapped into this option T here, and now we can actually use our computations and chain them together in a for comprehension without calling this flat map for option function. Okay. So now back to the question I posed earlier: when do monads transform? And the answer is it's difficult. Unfortunately, I really can't answer that question. I can just give you some heuristics. So what I think is that most data types, like list and option and trees and something like that, they compose. So you can write monad transformers for them. But for things which are not actually existing data in the memory, you can't, but sometimes you can. So functions, for example, the function monad, you can have a transformer for that. You can also have a transformer for the state monad, but you can't have one for the future monad. So you couldn't possibly write a transformer for future. And the reason is that the transformer would need to inspect the structure of the future. And you can't really, future doesn't really have structure. It's just it's something which runs somewhere. And if you would want to inspect the structure, you would need to wait for it to complete, and you don't want to block on futures, obviously. Okay, so to recap, monads are awesome, but often too powerful. As I showcased earlier, so you can't get error accumulating behavior with monads. Functors compose, applicatives compose, but monads do not compose in general. No, repeat after me. But specific monads do compose, and these specific monads come up very often. And when they compose, your code is 20% cooler. And this is the end. Mr. T approves of this message. Questions? Any questions?
You showed that in the gas library there's more transformer for option. Which more there exists there?
Okay, so the question was what other kinds of transformers exist in the CATS library. And I actually think I have Wi-Fi, so we can have a look. So the heuristic is everything which ends with a capital T is a transformer. A second. So this is the CATS library. So we can have a look. It might even be in its own. Wait a second, where is it? So let's have a look for option T. So it's actually in a data package, and we can have a look here. So what do we have? We have option T, we have streaming T, we have writer T, which is for logging. Actually, streaming T is kind of, you can imagine it like an infinite list. It's kind of the Scala standard stream on steroids. So you can have on every continuation you have an effect. So you can have a stream where every new cell requires evaluating a future. So you can have 1 and then a future of 2 and then a future of 3, something like that. And then there's XOR T, which is just the transformer for either. And also, exception to the rule, there's also Kleisli, which is the transformer for functions. And it doesn't. Yeah. And it doesn't end with T. Sorry, but yeah. So there are a couple of them already there. More questions? Yeah.
So transformers you use them for composing it, for combining effects, which is different effects related to the different monads.
Yeah.
There are other options for combining effects, for instance, coproducts. When do you recommend to use one of those?
So the question was, you can use monad transformers to compose effects. So just to reiterate this point, so option you can see that as an effect as a failing computation, and future as the effect of delaying computation. And with the option T, you can stack both effects together. And the other way to combine effects is using coproducts. So you can say I have a free monad, and you have different kinds of effects in there, and you put them together with basically a huge either or coproduct. And there's also another way, which is just called effects, which is a library. I'm not sure if it's initially from Idris, but there's an implementation for Idris.
There's a paper which is called something about F, and yeah, it's not really original for Idris.
Anyway, so yeah, it is available in Interlude. And all of these things have different characteristics. So in monad transformers, you get both effects of both the monads. If you use coproducts, you have either effect, one or the other. And with effects, with EFF, I don't know, you also get them, but the implementation is kind of different, so the ordering depends on the ordering of effects. So this is rather complicated. We can talk about this later. Anyway, so the monad but to reiterate, monad transformers are not the only way to compose effects. There are other ways, and in most cases, you can't just interchange them. They have all different use cases. They overlap, but they are not equivalent. All right, then thanks.